All right, folks, so let's get started here. We left off talking about weak acids, weak bases, navigating our Ka tables, all right? And for multi-protic acids, we can, take off multiple protons, but the idea is, we can put them back on, and you have a substance then behaving like a base. And so within this last portion here, we had that demo where we looked at different salts where they could be either acidic, basic, or neutral. And so we have to look at the ions themselves and think about, okay, do those ions come from weak acids, weak bases? Because then we're looking at the conjugate acids and bases in those points. So within some of these substances, looking at the ions are important, and you want to think, do they come from neutral sources? So when you neutralize a strong acid or strong bases, you get a neutral salt. So something like KBr, sodium chloride, those are neutral, while these components, because NH4 comes from ammonia, NH4, and we saw this, is actually slightly acidic. KCN, slightly basic, because cyanide ion comes from cyanic acid, which is a weak acid, so it is slightly basic. So let's look at a little bit more challenging one, something that's a polyprotic acid like carbonic acid. If we think about carbonic acid, that's H2CO3. But what if we have NaHCO3? So this is sodium bicarbonate. So what you see here, this HCO3, do you see how that is the conjugate base of H2CO3, that we took off one proton? So that whole HCO3, when there's only one hydrogen, is a total negative charge. So essentially we have this going on, so HCO3. So this process, going from carbonic acid to bicarbonate, we can describe that value as, that relationship as Ka1. So the equilibrium to take that first proton off, right? To make our bicarbonate anion, that conjugate base. And so the tricky thing here with this question is bicarbonate, because there's a missing proton, but there's still a proton there. Can't HCO3 minus, can't that behave like an acid as well? Can't we take another proton off? Right, so it can behave like a base. So we can write that equation. So I'm not gonna write the whole equation, but if that bicarbonate ion takes off another proton, so this would be CO3 2 minus, what equilibrium describes this conversion? If we looked it up, would you look at Ka1? You would look at Ka2, yes, Ka2. Right, so that's the subsequent steps to take off those protons. But where things differ, okay, is, well, what if we move backwards? What if we have CO3 2 minus? Can that act like an acid? CO3 2 minus, the carbonate, and no, it can't, because there are no protons. So CO3 2 minus can only act like a base. So when we go the other way, when we want to talk about CO3 2 minus acting like a base, we don't use Ka. We don't use Kas anymore. We use Kbs to describe this. So this, I wrote A anyway. This relationship we call Kb1. It's the first proton being added from the full conjugate base here. And so what you are seeing here is that Ka2 and Kb1 are related to one another. If we multiply those two numbers together, if we actually looked them up, if we took this times, oh, I wrote 1 again. I'm sorry, this should be a 2. That should be a 2. This is a 1. If we multiply these two numbers together, do we get a special number? Kw. We would get Kw if we multiply these two numbers together, right? And so when we have CO3 2 minus acting like a base, if it gains a proton, we get this bicarbonate back. Then we can go one more step. Okay, bicarbonate can also behave like a base, right? There's still room for one more proton to be added back on. So we can write another Kb value, but in this case, it's called Kb2. So do you see how this relationship is kind of backwards here? But the important thing is that if we take these two pieces of information, Ka1 times Kb2, we will get, if we multiply those two numbers together, Ka1 times Kb2, we would get Kw. So those two numbers are related to one another. And so, all right, so why did I write all of this? How does this help us answer this question? We want to predict whether NaHCO3 is acidic or basic. So we are looking at this substance, right? So I want to know, is it going to be acidic or basic? So if this substance is acidic, like if it loses a proton, which K value am I looking at if I want to describe HCO3 minus behaving like an acid? Ka2. That's the number you want to look at to decide whether it's acting like an acid. But the thing is, we're trying to decide, is it going to be an acid or acidic, or is it going to be basic? So also ask yourself, what is the equation that describes HCO3 minus behaving like a base? Which K value? Kb, but which one? Kb2. Kb2, that's the direction of HCO3 minus acting like a base, because when something's a base, it's accepting a proton. So ask yourself, in which direction is HCO3 minus accepting a proton? It's this direction. It's not, and this is the misconception. People will compare this value to this value. This value describes carbonate acting like a base, not HCO3 minus acting like a base. So these are the two numbers we actually want to compare to figure out whether this substance will be acidic or basic in solution. All right, so let's look at Ka2. All right, so where is this? Carbonic acid right there. So there's Ka2. So just based upon that number, is that a big number, a small number? It's pretty small. So do you think HCO3 minus is going to act like an acid? No, this is a pretty crap acid, okay? Crap acid. So let's just check our work here and get Kb2. Oh, but I don't have Kb2. I don't have a table with Kbs. How can I get Kb2? I have to get the K value, but which one? I have to take Ka1 and convert that to the Kb value of it. So that would give us Kb2. Polyprotic acids are a little bit tougher. I like single protic acids because there's only one value, but yeah, these ones are a little bit more confusing here. So we want to take that Ka1 value, recognize Ka1 times Kb2 equals Kw. So Kb2 is equal to what? Kw over Ka1. So 1 times 10 to the negative 14 over that number, 4.3 times 10 to the negative 7. So Kb is equal to, I don't know, something to the 10, okay, I'll actually do it. Something to the 10 to like the 7 or to the 8 or something. It's going to be a bigger number. And that's what I want to get at. That when we're comparing the correct Ka and Kb value, what we'll see is that when we calculate Kb2, Kb2 is 2.3 times 10 to the negative 8. So that's Kb2. So we compare that number to the Ka1 value, or sorry, Ka2 value from the table, 5.6 times 10 to the negative 11. We see that the equilibrium is larger for the base number, okay, Kb2, or sorry, yeah, no, Kb, yeah, Kb2 there. And it's a larger number, so then this substance, HCO3 bicarbonate, is going to more likely behave like a base because its Kb value is larger than its Ka value for that same, instead of, basically I'm saying because Kb2 is larger, it's more likely to accept a proton and produce OH, so be basic, versus donating a proton to water and making the water acidic because its Kb value is larger, that there's more products there for the base reaction. But let's just like go back to our intuition, like Na sodium bicarbonate is better known as, do we know what that's called? It's in our kitchens. Baking soda. Baking soda. Baking powder has aluminum in it as an acidifying agent. Baking soda is just pure sodium bicarbonate. And so it has basic properties. So oftentimes when you're baking, so here's a fun fact. The difference between baking soda and baking powder. Baking soda we just determined is what? Acidic or basic? Basic. We know when you mix baking soda and vinegar is an acid, you get neutralization, you get those bubbles, right? Baking soda is basic. So when you do recipes, all right, with baking soda, you need to have an acidifying agent in the recipe itself. It could be a lot of things. It could be lemon juice, it could be milk. Milk is actually a little bit acidic. And so oftentimes recipes, see the order in which you mix your acid and base ingredients in a baking recipe that calls for baking soda is actually important. Sometimes you might want to add your acidifying agent very, very last because those bubbles are what you want to produce when you neutralize baking soda, you get CO2. And so you want to add that acid last. So if you do that, like try it at home. That's just from the chemist in me thinking, okay, you want to make those bubbles as late as possible and then stick it in the oven so you get a nice fluffy whatever. You're looking at me like you're going to do it. You're going to try it versus just like mixing everything together, beating the heck out of it. Because what are you going to do? You're going to let all those bubbles out, right? Okay. That's baking soda. You need a separate acidifying agent because baking soda is just a base. Baking powder, if you look at the ingredients on it, it has a dry base and a dry acid component in it. I think it's like some type of aluminum something. So when you mix it with water, you have the acid and base component in it and you get the bubbles. So that's the difference between baking soda. Baking soda, you need the acid like separate in the recipe. Baking powder, you don't because it's already in there. It's like a bath bomb. Have you ever done a bath bomb? Okay. Can you imagine what a bath bomb is? You put the thing in the bathtub and it bubbles like crazy and then you like soak in it or whatever and you come out looking like a blue Smurf. So it bubbles. A bath bomb, when you buy it from Lush or whatever, bubbles in the bathtub because there's both an acid and base component in the actual like solid thing itself. It's actually, I think, citric acid and baking soda in it like already. And so when you put it in contact with water, it allows that neutralization reaction to occur. So it's all in there encased until you put it into water to allow it to happen, all right? So that's how a bath bomb works. So it has both the acid and base component in it. Okay, so there we go. All right, so this question definitely kind of on the harder side when looking at polyprotic acids. You want to see which K value is larger, but you want to be sure you're looking at the right one. Looking at the right one. All right, so let's do, I think the end of this chapter, we're just going to do a couple more example problems. And what's really pertinent here is we want to be sure we're using the right equilibrium expression to describe what's happening. But what you'll see here is that like the calculations for a lot of these, like what's the pH of this solution, they're literally all the same. Once we do a lot of them, you'll see that they're all very, very similar. We just want to make sure we're using the right K expression. All right, so I want the pH of a solution where we have 0.1 moles of sodium fluoride in 500 milliliters of water. So my strategy here is ask yourself, what is in solution? Is it acidic? Is it basic? What's that substance? So NaF in this case, do you see the Ka they give us? Did they give it to us for HF? HF? That's not this. That's not that. They give us NaF. So F minus is what? How is that related to HF? That's the conjugate base. So the common mistake that students will make here is they'll write, oh, they give us the K for HF, so I'm going to write the K expression for HF. This is the common mistake. They'll do that. You don't do that. Because this reaction is describing HF behaving as a acid. Is F minus an acid? No, it's not. We need to write an equation that describes F minus behaving like a base. So what equation will we use? K, not Ka, but Kb. Yes, so we don't want to use this reaction. No, HF is an acid. So if we write the equation, the Kb equation instead, it's F minus plus water gives us HF plus OH instead. There we go. So I'm going to just drop the states here, okay, because I'm lazy. Okay, so I wrote the Kb, but the question didn't give me Kb, like the number. Where do I get the number? From the, can I look it up on a table? No, I can't, but they give me the Ka value for HF. So you can get Kb from the relationship that Kw over Ka equals that. All right, so we have the number for this expression. All right, so now that we have the equilibrium set up, now it's an ice table. All right, ice table, recall what is the unit, or like the unit we need to put in it? Molarity. So they give us a mole amount. I don't want to put mole amounts in. You put mole amounts in for BCA tables, for reactions that go to completion, but for ice tables, we need them to be in molarity. So the molarity of this NaF solution is what, 0.200? Agree? Okay. So that 0.200 molarity number is going to go in which line? Which line? Initial, yes. So I'm going to put it right here, so 0.200. We don't care about water because that's a liquid. It's not going to be in the Kb expression anyway. HF is 0, OH minus is 0. What do we do next? I don't want to put it next there. I'm just going to scribble it out. The next step is doing the change. So how do we set up the change line? Left to right. This reaction has to go in what direction? Towards the product. So it's minus X for fluorine, or fluoride, sorry. It's minus X for water as well, but we don't care about that because it's not in the equilibrium. But then it's plus X for HF plus X for OH minus. And so we see in the equilibrium line, it's 0.2 minus X, X, X. I hope you see, for like almost every weak acid, weak base problem, you get a K expression that looks like X squared over concentration minus X. Have you done enough of them already and you see it's the same frickin' thing every single time? Okay, so if I set up my Kb expression where it's this times this over the F minus, we get X squared over 0.2 minus X equals the Kb value. I'll just quickly calculate Kb. Kb equals 1.4 times 10 to the negative 11. Okay, so this whole thing is equal to 1.4 times 10 to the negative 11. All right, so there's my Kb. What's next? Solve for X. Okay, so the method we use here is that we can usually neglect X, in this case on the denominator, because K is really, really small. K is really small, so we're not going to be losing a lot of, we're not going to be losing a lot of substance right here. X is going to be really small. So I'll be able to neglect that. And so what we'll get is X squared over 0.2 molarity equals 1.4 times 10 to the negative 11. And so we get X equals 1.9 times 10 to the negative 6. Is that my answer? Is that my answer that I put into my Carmen quiz? No. Look at what the question wants. It wants the pH. X equals what? Look back at what we assigned X as. It's the concentration of OH minus. OH minus. So look back at what we assigned X as. When we did the weak acid ones, X, when we used a Ka expression, I hope you see this. When we, like if we pretended this was HF instead, like we were adding the acid instead and we use Ka, X equals concentration of H plus when we use a Ka expression. But when we use Kb, X equals the concentration of OH minus. So this is equal to OH minus. So do recognize, like, what did we assign X as? And because this is Kb, it's the concentration of OH minus. So if you take the negative log of that, the POH, that will give us POH, is something, 5.72. And so then it's one more step to get that the pH is equal to 8.28. All right, so it's 14 minus that. Do we see that? You see that? So we will be doing this over and over and over. X squared over like the initial concentration minus X equals Ka or Kb, depending on what substance you have. Let's do the calculation. Let's pretend I misread the label. Let's do one more. Let's say it's the same exact thing. We have 0.200 molarity, but this time of HF. What's the pH? Let's just do it for fun. So it's the same Ka value, but HF is acting like a acid, so we use Ka in this case. So we set up HF gives us H plus plus F minus. We do the ice table. So 0.200, the reaction has to go in what direction? To the products, so it's minus X, plus X, plus X. So at equilibrium, we have 0.2 minus X, X amount of H plus, X amount of F minus. We put together the Ka expression. We're using the Ka expression because we wrote the Ka expression. So the substance acting as an acid. So putting that together, we get X squared over 0.2 minus X, but it equals Ka in this case. What was the Ka value? 7.2 times 10 to the negative 4. All right. So typically with these weak acids or weak bases, we can usually neglect whatever that X on the denominator to just simplify it so it's not a quadratic, and it works perfectly fine here. So we get X, once you do that, I'm doing this off the cuff, so 7.2 e to the negative 4 divided by, times 0.2, take the square root of that, we get X equals 0.012 molarity. What is X? H plus in this case. So taking that number and doing the negative log of whatever gives us the pH. This will have a pH of 1.92. Do you see how we set this up? It looks exactly the same as this one. It's just the difference is we set it equal to Kb. X is equal to a different variable. It's OH when it's we're talking about a base, but it's equal to H plus. That X is equal to H plus when we're talking about an acid. So you want to be really aware of what you're putting in solution. I have a couple more examples where we will just set up the equation, but not actually calculate it, because what you'll see, it's the same freaking thing over and over and over. And this is really important when we get to chapter 17, the next one, because we're going to be doing this even more. All right, so let's do another question here, the HN3 sample. So this is another way I can ask a question. I gave you initial concentrations, you calculated pH. Here, I give you a different way I can give you pH, kind of. Because the idea here is if I give you a pH of a solution, what does that pH tell you? Like, what piece of information from the ice table does that tell you? It's the H plus concentration at equilibrium. So here's another way I can give you that piece of information. So here I have this acid, it's 2.2% ionized, calculate all of the equilibrium concentrations. So I'm just gonna call this HA, because I'm lazy. So because this is an acid, so we have HA goes to H plus A minus. We're gonna have to do a ice table. They give us the initial concentration, so that's nice, so 0.04. Now we need to work with this, what the heck is this percent ionized number? So percent ionization, remember, and I believe I give this to you on the supplemental sheet, your percent ionization equals your concentration of H plus at equilibrium over your acid initial. So essentially what you're doing is you're taking this at equilibrium, it's this whatever H plus or how much A minus you make over the amount of stuff you started with initially. That's how much ionized. I'm saying, oh, 2.2% of your original stuff ionized to H plus. And so what we see here is we are given the percent ionization, 2.2. Oh, this is times 100. We all have the initial concentration. So look, this is just another way we can get H plus concentration at equilibrium. It's just a different way of saying that. So putting this together, we can get that the H plus at equilibrium equals 0.022 times 0.04 molarity. So what is that? 8.8 times 10 to the negative 4 molarity. Okay, so let's finish our ice table. Ice table, all right? So same exact deal here. We start with 0.4 of our acid. Our change line is minus X plus X plus X. So our equilibrium line is 0.04 minus X, X, X. Putting together our Ka expression, it's X squared over 0.04 minus X where do we go to next? Can we solve this? Do we solve for X? No, we don't. Because this time, this question's phrased a little bit different. This time we are actually given X, what X is. What is X? It's H plus. I gave it to you. So we just calculated it. So we're actually going to put this number we just got, this H plus value, that is actually equal to X. I didn't, pull this out of nowhere. It came from our ice table. At X, at equilibrium, is equal to H plus concentration. And that's what we just got. So the next step here is to just plug that into our Ka expression, and we can get our Ka. So it's 8.8 times 10 to the negative 4 squared over 0.04 minus that number, so 8.8. And you can see it's like a small number, so it's barely even going to change that denominator. And so what you get here is that Ka equals, I think, 2 times 10 to the negative 5. Good. And it says, what are all the concentrations of everything at equilibrium? How would I go about doing that? Just plug in X into the equilibrium line. And so you'll see that that H plus we already got, and it's the same concentration of A minus because they're both equal to X. And then to get HA concentration, you just do what we started with minus the X amount we got initially. But I think you see that it barely changes. It barely changes. Bless you. Let's just check this acid. So that's our Ka value. I don't know if I checked this before. Do I have, give me a second. Handouts, chapter 16. Is that acid on here? Yes, hydroazotic acid right here. What's the Ka value? Are we close? Yes, we are. 1.9 times 10 to the negative 5. We got 2 times 10 to the negative 5. Great. Love when that happens. All right. So what else? Okay, let's do one more. A solution of acetic acid has a measured pH of 3.45. What is the molarity of this solution as written on the bottle? So what this is asking for is the initial concentration. So I want you to think about what substance is in our beaker. Acetic acid. It's an acid, so we want to write which equation? If it's an acid. Ka. We want to write the Ka for this substance because it's an acid. So I write Ha gives us H plus plus A minus. Because this question would change. Like you might say, oh, look, no, Dr. N, they gave it me Ka. Of course I'm going to write the Ka expression. But what if this wasn't acetic acid? What if this was sodium acetate? You could still answer the question. I want you to be thinking about what is in your beaker. That's going to dictate which K expression you need to write. This is an acid, so we need to write the Ka expression. All right, so what pieces of information do they give us? They give us the pH. So this number tells us what on the ice table? H plus at equilibrium, or better known as what variable? X, when we put it all together. So this one, like typically we put a number right here under HA, but we don't know it. So I'm just going to call it N. I don't know. I'm just going to call it N. And I recognize that, we have the same change that we always see. So the concentration of HA at equilibrium is N minus X. H2 is X. A is also X. But the idea here is that X, because it's equal to H plus, and I'm given the pH, I know that number. It's 10 to the negative 3.45. That's what X is. And so now you can set up your Ka expression. Ka, and we know that number. It's 1.8 times 10 to the negative 5 equals X squared N minus X. I know what X is. So 10 to the negative 3.45, that squared over N minus 10 to the negative 3.45. And so here, see, we only have one variable, N. We know what Ka is, just solve for N in that case. Got it? Yeah? And so we solve for N in this case. N is equal to 0.0073 molarity. So if I make up a 0.0073 molarity solution of acetic acid, I let it come to equilibrium, and I stick in a pH probe, we should get a pH of 3.45 based upon its Ka value for acetic acid there. All right. Those are basically all the types of questions I can ask you. This is really critical, determining what is in your beaker, what K expression to use, how to solve for X, what does X mean, and how can we get pH. That's critical for chapter 17. All right, so in the next slide here is the strategies on all the ways we can calculate pH. All right, if we're given a strong acid or strong base, those ones are easy, right? We just assume all of the H plus dissociates or all of the OH dissociates. We just take the straight concentration, plug it into pH or POH. That one's easy. It's when things are weak is when it's hard. Recognize I can either give you an acid, so like HA. If I give you an acid, like a neutral acid, something like HA, you use Ka for that because HA is going to act like an acid. But if I give you a neutral charge base like B, so something like NH3 or something, you use the Kb for that substance. All right? And then the difference here is you go through the ice table, you solve for X. X might mean different things. In our Ka expression, X is equal to H plus concentration, but if you use Kb, X is equal to OH concentration. In all of those cases, we almost always neglect the X in the denominator, so it's not a quadratic. Do you like neglecting X in the denominator? I hope you do, yes. Okay, so the idea here, what I just mentioned, if it's Ka, X will equal H plus. If you're using Kb, X equals OH minus. And this is, you might be asking, well, why? It's because of what the expression for Ka or Kb, what it means, what we assign X as. And as you do more examples, you'll see it come up over and over. All right, so those are neutral weak acids or weak bases, so HA or B, like NH3 or something. Where things get even more difficult is recognizing, well, I don't have to put acetic acid in water. I could put sodium acetate in water. Acetate is the conjugate base of an acid. So the calculation differs a little bit, okay? If we're adding a conjugate base into water, then we need to use the Kb expression. We get that Kb from the Ka from its original like acid source. But then it's all still the same. So here, conjugate of a weak acid is a base, a weak base, so something like NaF. You would use the Kb expression for from HF. So you'd calculate Kb from Ka of HF in order to do that calculation. So if you were plugging into a Kb expression, when you go ahead and calculate X, X is what? OH, because we're working with Kb, not Ka. So this is our OH concentration, all right? Versus we do the conjugate of a weak base, which is a conjugate acid, okay? So something like NH4 plus. So see how we went from like the base, the neutral base, but what if I put ammonium in solution? This is an acid. So we want to actually use the Ka. We want to describe NH4 plus acting like an acid, which is Ka, but that comes from the Kb of NH3. But we plug in the known numbers into the Ka expression instead. So when we calculate for X, X equals what? H plus, yes. So for all of these examples, these last two, when you set up your ice table, your equilibrium line, and you stick it into either Ka or Kb, you will always see the form X squared over the starting concentration minus X equals K. Every single time, every single time. The detail and the subtlety is understanding, well, is X H plus or is X OH minus? It changes depending on what substance you have in solution. All right, okay. So I really hope you can recognize that here soon because it's all coming together in chapter 17. Okay, so before we move on, I just want us to recognize what strategy to use for these different solutions. So I'm gonna give you different substances, okay? And we're gonna predict what K do we use, okay? And then how do we calculate pH? So I have the Kas here for you, all right? So if we have 0.10 molar HCO2, so that's that's chlorous acid. How do we get the pH? How do we get the pH? What do we use? So I have the tables here. What do we use? Hypochlorous acid, or sorry, chlorous acid. Ka. Where is Ka? What is it? 1.1 times 10 to the negative 2? So how we set that up, how did we know to use Ka? It is a weak acid. Yeah, so we use Ka, and how, if you go through all the ice table stuff, you'll get that your equilibrium line ends up being X squared over, what goes on the denominator? 0.1 minus X, but we usually neglect that bottom X, okay? When we solve for X, what is X? H plus concentration, and then you get pH. Okay, cool. The next one, ammonia, 0.1 molarity ammonia. What K do we use? Why Kb? Ammonia is a weak base. Also, if you look up ammonia on these charts, It only shows up under the Kb numbers, right? That's like another, like you won't find a Ka for ammonia, right? Yeah, so we use a Kb expression instead. How will that expression end up with our ice table? Kb equals x squared over 0.1 minus x. I hope you've seen, we've done like enough examples where you see it's like the same thing over and over. But the only difference here is when we calculate for x, it's equal to not H plus, it's actually OH minus. And again, it's all because of the Kb expression. I'm just skipping those steps, all right? We've done like many examples of all of these using either Ka or Kb. All right, and then from OH concentration, you can get POH, then pH. Okay? All right, so let's keep going. What if we had 0.1 molarity sodium chlorite? What's the pH? What is it? Now it gets harder, because I can't find sodium chlorite on the table. What do you have to recognize? ClO2 minus is what of what? Conjugate base of HClO2. Yes, so like if you look back here, see how this is the anion of the acid that the first one that we did. Okay, so is ClO2 minus, is that going to act like an acid or a base? Base. So do we use a Ka expression? No, we need to use Kb. But where does that come from? I don't see that substance on the Kb chart. Where do I get Kb? From the Ka of its original acid. So it's this Ka right here. We already got it. It's right there. Okay, it's on the table. So we use that Ka to get Kb, but we still set it up like any Kb expression that we've done before. It ends up being x squared over 0.1 minus x, but when we calculate x, it's the concentration of OH minus, and we get POH, then pH. The trick here is in this third one is that in order to get the correct, students will want to use the Ka expression, but you don't. Use Kb, but it comes from the idea that Kb is equal to Kw over Ka of its like original acid, HClO2. Are we seeing it? See, on Monday, I saw just the life in your eyes just disappear. I don't think it hasn't come back yet. All right, the next one. NH4Cl, NH4Cl. What is it? It's a conjugate acid of NH3. So it's an acid, right? So we need to use a Ka. Where does the Ka come from? It comes from the Kb from ammonia. NH4 plus is going to act like an acid. So we do Ka equals x squared over 0.1 minus x equals the Kw over Kb for NH3. Right? X is equal to H plus or OH? H plus? Yes, H plus. Yeah, because this is Ka. Yes, and then you get pH. Okay, let's keep going. This. Ka or Kb? Yeah, there's a lot of letters there, but really it's no different than like NH3. It's just like a methane instead of an H. So this is most likely a base. So we're going to use Kb in this case. When you solve for x, what is x? OH minus. Okay, how about the next one? Yeah, ooh, there's a lot of letters in there. But I put them right next to each other. Is this spinach garbage mess, is that an acid or a base? See, if this is the base, I should do a different color. This is the base. That's the base. Do you see the base in here? Oops, sorry. Do you see the base and see how there's a hydrogen attached on? So what we're seeing here is BH plus. So that is the conjugate acid of the base. So we're going to use Ka in this one. The Ka comes from where? The Kb of this one, which you can look up on the table. All right, and then Ka, when you solve for Ka, or you get X is H+, you calculate pH. Okay, the next one, benzoic acid. Ka or Kb? Do we set up Ka or Kb for benzoic acid? Ka, yes. Why Ka? Because it's an acid. Is this, are you getting it or not? Like, it's like, I just hear deafening silence. You do see it, you see it. So we use Ka here because it's an acid. When we solve for X, X will be H+ concentration. Because we use Ka, yeah. That one? Yes, so this is a base, it's on our table. So you were scared of it because there's a lot of letters in it. But it's so here, okay, there's that. So if we look at this table, so do you see ammonia here, right there? That's ammonia. See it? Ammonia, it has nitrogen and 3 hydrogens on it. There's a lone pair. So some of these other bases that you see, like trimethylamine, ethylamine, what I want you to focus on is this nitrogen. See the nitrogen there? And we just have 3 things attached to it. They just happen to be different things. When it's hydrogen, it's nice and clean looking. But when it's carbons, it's dirty looking. And it's harder to see the base within there. So do you see nitrogen is right here for the last one, trimethylamine, which is a base. What's attached to it? 3 what groups? These 3 carbon groups. Do you see the CH4? So it looks like this, CH3, CH3, CH3. See, there's 3 of them, and then there's a lone pair. Do you see how this, this looks basically the same as this. It's just there's a carbon group instead. But I want you to recognize that it's still a base because of that nitrogen. So imagine if you wrote or drew the conjugate acid. If you draw the conjugate acid for ammonia, don't you just put a hydrogen right there? So if we draw the conjugate acid for this, it's the same thing too. So we just tack on a hydrogen at the end. So let's go back to the actual question here. See how this looks very similar to ammonia. I just drew the H's on the other side, so you can see there's just 3 things attached to nitrogen. So when we draw ammonium, we usually call it NH4, but because instead of 3 hydrogens, they're methyl groups instead, do you see that hydrogen tacked on at the end right there? And it's attached to a nitrate because this whole thing is positively charged. Do we see that? Okay. Yeah.
So why don't we focus on the nitrate number?
Did you answer your own question? Yeah, if we had something like sodium chloride and I asked you, is that neutral, acidic, or basic? You would say neutral because chloride comes from HCl, which is a strong acid. So it's the same idea if I asked you, is NaNO3 neutral, acidic, or basic? You would think, okay, NO3 minus what's its like acid that it comes from? HNO3, which is a strong acid also. So yeah, we don't have to look at NO3. What you'll see here is you'll often see chlorides and nitrates attached to things, and you're focusing on the other stuff for like either it being a weak acid or a weak base. All right? Okay, yes, okay. Benzoic acid, we use Ka. What about sodium benzoate? What do we use? So if benzoic acid is Ha, what would the formula of sodium benzoate be? NaA. Because can I just take benzoate ion off the shelf? No, it always has to be attached to something else to make it charge neutral. And oftentimes we'll use sodiums or like chlorides or nitrates to do that. So sodium benzoate, we use Kb, but it comes from the Ka of benzoic acid, its conjugate, or sorry, its acid form. So you calculate that from Kw over Ka. Okay. Good. All right. You need to do more practice. You need to do more practice. All right. So we are moving on to chapter 17. So that means chapter 16 homework is due on Sunday, but because of the holiday, I moved it to Tuesday at midnight. Okay. But you need to do it. You need to do it. Okay. You need to be doing these ice tables because it's just going to get worse. It's going to get worse here in a little bit. All right. So we are going to, this is the last chapter of chemical equilibria. We're tying everything together and we're looking at all the weird exceptions or all the weird scenarios. Because up until now, we've only put in just a weak acid into water or just a weak base into water. And now the idea is, well, what if we mix the two? Right? What if we do a titration and we partially neutralize our weak acid to a weak base? That's a buffer. So we're looking at all the weird scenarios. So everything we learned in chapter 16 still stands. We're using all those same equations. The only new equation is this one that we're looking at. This is the Henderson-Hasselbalch equation, which is really just the Ka expression where we take the negative log of both sides. That's all it is. So yeah, pH equals pKa plus log base over acid concentration. This is how you calculate the pH of a buffer. That's the only new equation, but we're still building off all the equations we did before in chapter 16. So we're still working with equilibria. We need to be thinking, are we working with an acid or if we are working with a base? Because that will dictate whether we use Ka or Kb. And so basically, when we do a titration, so here you see pH being graphed with volume of titrant added. We have all acid before we start the titration. How do I know that I'm starting with an acid in this titration curve? How do I know I've been starting with an acid? The pH is low. Yeah, it's acidic. Right? And then as I neutralize it, you see that the pH slowly starts going up, but it's not linear. And so we're going to inspect those different regions. You actually already know how to calculate every single region, except this part. Except this part. You know how, like if you think about what is in your beaker, you know everything that's in there. So right here, if I only have HA in solution, what do I use? Ka or Kb? Ice table. Ka. What if I neutralize my substance, meaning that I've converted all the HA into what? If I neutralize it. Let's remember neutralization reaction. So HA plus NaOH. What are my products? So note the arrow. It's like a full reaction arrow. How do I neutralize that? Yeah, I get NaA. I get the salt and water. NaA plus H2O. So at the equivalence point right there, at the peak, the inflection point of this titration curve, what is in solution? If I've neutralized it, just right here. I wrote it. We have NaA. You know how to calculate that. If I know the concentration of it, how do I calculate the pH? What ice table do I use? Do I use Ka? You use Kb. That Kb comes from the Ka of the acid you started with. Okay, and so the only new part of information is the buffer region, which we'll look at, which is the common ion effect. And actually, so let's pretend you add a little bit more acid, or sorry, a little bit more base, like you go past the equivalence point where, you know, moles of acid equals moles of base. Now you have too much base. Once you're at the point of too much base, it's just a strong base pH calculation. You just calculate how many moles of base you have. That will give you the pH. You literally know how to do every calculation already. All right, so let's go into it. Oh, and this is, we just talked about this, all right? How to calculate pHs depending on what is in your solution. I'm telling you, knowing how to navigate what strategy to use depending on what's in your beaker is very important right here. All right, for a strong acid, strong base, it's just pretty straightforward. Get your H plus or OH that's left over, just plug that in. For weak bases, we usually do an ice table, x squared over initial minus x equals, you just have to decide, is it Ka or Kb? And then it gets a little bit more complicated if we have a conjugate. It's still x squared over initial minus x. Again, you just need to decide, is it Ka or Kb, and how do I get that number that I need? All right, so the weird exceptions, sometimes we're gonna have multiple acids in solution, all right? And so the idea here is if you have multiple acids in solution, we oftentimes will just focus on the one that's the strongest. All right, so when you have multiple things, and we kind of looked at this already when we looked at bicarbonate, we said that it was a better base than it was an acid because its Kb was bigger. And so that is the idea here. If we have a solution that contains HCN and HNO2, we will actually just use the ice table for nitrous acid because its Ka is bigger. That it's going to contribute the most to H plus concentration because it's the strongest acid. But what if I have a mixture of HCl and acetic acid? How do you think, based upon that, if we're always looking at the strongest substance to calculate pH for our ice table or whatever, if we have a mixture of HCl and acetic acid with that Ka, how do you think we'll calculate pH? Do you think we'll use an ice table? If I tell you, we always focus on the strongest acid. The strongest acid. Which is the strongest acid there if we have a mixture of HCl and acetic acid? HCl. So are we going to do an ice table? No, we'll actually just figure out, okay, how much H plus is HCl contributing? That's going to give us our pH. All right, so in this case, we'll assume that essentially acetic acid is not contributing at all because it's a weak acid. And this is an assumption we're making, and it's fine for this class. If you take higher level class, we will look at coupled equilibria, and that sometimes you can't do that. But that's outside the scope of this class. So yeah, for this one, you're just going to assume, and we'll do this for our titrations, that the concentration of HCl is equal to the H plus total. So we're neglecting acetic acid, essentially, because it's weak. And it's not going to be giving up its protons as much and making a big difference, all right? This strategy also applies for polyprotic acids. So the idea here is like if we put phosphoric acid in water, H3PO4, that first proton's going to come off, but we can typically ignore the Ks, like Ka2 and Ka3, because they're much weaker, all right? And that's why we say, oh, these protons come off one by one. And the reason is because the Ks get successively smaller. And so we can kind of neglect them. We want to look at the strongest one, meaning the one with the smallest negative sign because there's less zeros there. Okay, so that's multiple Kas, but we've kind of already been doing that a little bit, but I'll show you an example where things break down. Okay, so we're going to look at the common ion effect. So the idea that we might not just have pure, pure acetic acid in water. We might have other stuff happening in water as well. We might add other things, and this gives rise to the common ion effect. Okay, so I want to propose this, and I think I might blow your minds. So what is the pH of a solution with HCl equal to 1 times 10 to the negative 3? Remember what how to get pH for a strong acid. So I hope you recognize this is a strong acid. It's HCl. So when we plug that into our negative log concentration, you just plug that in, that'll give you pH. What is the pH? 3. Yes, it is 3. Whoops, sorry. Is it acidic or basic? Acidic. For 2 reasons, right? Like we added an acid to water. It should be acidic. Also, the pH is less than 7, so it's acidic. Do the next one. You have a solution of 1 times 10 to the negative 8 molarity HCl. What is the pH? 8. Is that solution acidic or basic? Does that make sense? Does that make sense? HCl is a acid. It's an acid. You put it in water, and it became basic, or the wheels turn. Does that make sense? I hope you have question marks over your heads right now. That should not make sense. So there's an assumption we've been making all this time that now I will unveil the curtain, okay, behind what is happening. So we've been making an assumption all this time that when HCl dissociates, you get, 1 times 10 to the negative 3 H plus. That's your pH, like you plug that into pH, that all the H plus is coming from HCl. That's the assumption. Things break down when things are really dilute, really, really dilute. So like this, like 1 times 10 to the negative 8, that's really dilute, right? Okay, and that's why we get a number that doesn't make sense. It should not make sense. That doesn't make sense. No. It should be acidic. It should be less than 7. So what we're actually neglecting is that there's actually 2 sources of H plus in water. There's HCl and there's water. Water undergoes autoionization, Kw, where we have water turns into H plus OH minus. So that is what we are neglecting, right? So we need to actually consider the autoionization of water for really, really, really dilute strong acid or strong base solutions. So really, we've been assuming all this time, right here, we've been assuming this, that the HCl, the total H plus is just equal to H plus coming from HCl, but that's not true for dilute solutions. So what's true for really, really dilute solutions is we actually have to consider the H plus that's also being produced by water. And this matters because when things are really, really dilute, because when we, remember when we solved for our autoionization of water and we got the pH of neutral water, what was X in our ice table when we calculated this? 1 times 10 to the negative 7. Yeah, because we set this equal to, it became X squared equals KW, so we got X equals 1 times 10 to the negative 7. So once we get to H plus or OH minus concentrations of the thing added close to the negative 7, that's where things start to break down. So let's actually calculate what the pH of the solution is, and it actually makes sense. So what is happening is the common ion effect, is that we have a water equilibrium, all right, this one, right? This is our Kw expression, it equals that. But we add acid to it. So we're gonna say, oh, this H plus that we're adding to water is an initial concentration. So that's actually gonna go right here in the initial line for H plus. We're contributing a little bit of acid before doing this autoionization, right? So the idea here is we're gonna stick that right there. So 1 times 10 to the negative 8. We have 0 OH, we have 0 water, but doesn't matter, it's just a liquid, so who cares? Or actually, no, we don't want 0, we want N, an N amount, right? And so what happens, water breaks up a little bit, okay? So we subtract X, we add X amount, we add an X amount. And so at equilibrium, we have an N minus X amount of water, but it doesn't matter because it's a liquid. It won't go in K anyway. H plus at equilibrium is 1 times 10 to the negative 8 plus X, and then OH is equal to X. Okay, what next? Once we have our equilibrium line, what do we always do after our equilibrium line? Plug it into K. In this case, KW. So I'm going to plug that into my KW expression, equals, KW equals just H plus times OH. So I'm going to take that equilibrium line. It's 1 times 10 to the negative 8 plus X times X equals 1 times 10 to the negative 14. All right, so in this case, you just have to do the quadratic, because these are really small numbers. You have to do the quadratic, but it's not that bad. Quadratic. All right, I think A is 1, this is B, and then like C is negative KW in this case. So once you do the quadratic or put it into Wolfram alpha, you get X is equal to 9.5 times 10 to the negative 8. Is that our answer? We're trying to get the pH. That's not our answer. What is X? It's what? The concentration of OH. Where did I get that? The ice table. Yes, that is the concentration of OH. But now you can see how we can get pH, right? So I can convert, I can take this number, right? That's OH concentration. We can get POH, and we can get pH. Put that into your calculator and tell me what you get. I'll do it too. Negative log 9.5 e to the negative 8, but recognize that that is your POH, so it's 14 minus that number. So my POH ended up being 7.02. pH equals 6.98. Does that pH make sense? What did we add to water? Acid. The pH of the water should go down. Did it? Yes, it did. Fantastic. Good. So now this is how we can calculate the equilibrium or the pH of a strong acid that's really, really, really dilute. All right, and we have to consider the self-dissociation of water in order to do that. So the idea here is we were neglecting the contribution of water. So essentially that X term that we got, that's how much H plus is coming from water itself, this term. So when we do really, really strong concentrations of HCl, like 0.001 molarity H plus, we can typically ignore what's coming from water. Why can we ignore that? It's because it's a really, really small number. This number is usually around 1 times 10 to the negative 7. If you add this number, 1 times 10 to the negative 7, to this number, is it going to change it? No, it's not. That's why we can neglect doing the autoionization of water for really strong concentrations of acid or base. It's when things are really dilute, we can no longer ignore this part. All right. So if we compare, so if you do the X calculation, right, for pure water, here you get X equals 1 times 10 to the negative 7. That's of regular pure water. But when we calculated it using our common ion effect, X ended up being a little bit smaller than normal. Do you see that? It's times 10 to the negative 8 instead of negative 7, so it's a little bit smaller. So this is kind of leading us to the idea of the common ion effect and how we can shift equilibria around. We can take something that's already at equilibrium, so something like water, we add a little bit of H plus and it pushes the reaction to the other side. So let's look at the equilibrium of pure water. Pretend this water, we have pure water at equilibrium and we add a little bit of H plus. So this goes back to, I think, chapter 15, right? So we have an equilibrium, we add a little bit of product. Which way does the reaction go? To the reactants or products? Reactants. Yes, it pushes to the reactants. When we push to the reactants, we make more what? When we push to the reactants, we make, according to the reaction, don't look at me, look at the reaction. What do we make more of? Water, H2O. But in doing that, when we make water, what do we also have to consume? H plus and OH minus. So when we consume OH minus, shouldn't the pH go down? It should become more acidic, and that's what we saw anyway, right? So that's kind of an example there. We add more H plus, we make more water, and so we consume some of that extra OH that's dancing around there. All right, so that one's a little bit more abstract. I actually have demos here to show exactly what I'm talking about, okay? So this equilibrium, we have acetic acid, and we have acetic acid and water, right? So like vinegar, we have vinegar and water. And the idea here is, what if we start with acetic, like pure acetic acid first, or an aqueous solution of acetic acid? What happens when we add sodium acetate? So we're adding A minus here. So same idea, if we add product, which way does the reaction go? To the reactants, it's going to go this way. When we go to the reactants, what do we also do? Consume H+. So if we consume H+, which way does the pH go? Does it become more acidic or more basic? Basic? Yes, because we don't have as much H+ floating around. So it's weird. We can add conjugate base and we affect the pH because of this Ka equilibria. Let's do the demo. Okay, gotta do this. Okay, so there we go. You see that? Okay. Oh, this looks awful. Whatever. Okay, so there we go. What you see here are 3 beakers. One of them, 2 of them are just for a reference, all right? So we see this blue beaker. See the blue beaker? So this blue beaker just has pure water in it with an indicator. So if this is pure water, what's the pH? 7. Okay, good, 7. So that's the color it looks when it's pH 7 or neutral. Here I have, in these 2 yellow containers, I have acetic acid. If we put acetic acid in water, the solution should turn acidic, because acetic acid is an acid. So there's much more H+ floating around. So these are lower pHs than 7. It's acidic. So we just made a prediction that if I add sodium acetate, we add the product and it shifts to the reactants. And so in doing that, we consume H+. And so which way should the pH go when we add sodium acetate? It should become more basic. So if this is already acidic, it should turn blue. It should, right? Let's hope it does. I hope so. Whoops. Okay, can you see it? Yeah? Okay. I don't know how much to add. Go. Is that what happened? Let me add more. Let me shift it more. So we added the acetate anion. It shifted the reaction to the reactants. In doing that, we also consume H+, so it lowers H+ concentration, so it raises the pH. And so now we see that the solution is going towards more basic. Basically, going closer to neutral. You see that? All right, so that is the common ion effect. Basically, it's Le Chatelier's principle. Okay, let's do another one. So if we go a little bit further down the thing, okay? So what did we observe? Where's my pen? We observed it became more basic. Another way to think about it is we started with an acid. We added a conjugate base. We added something that was basic. So shouldn't it become more basic if we add a base? Yeah, that too. But based upon the equilibrium, we also see the same thing. Okay, this one's a little bit cooler, I think. Okay, so consider a saturated solution of sodium chloride. All right, we have we have sodium dissolved so much in water that no more sodium dissolves. This is actually an equilibrium. It's called KSP, where SP stands for solubility product. We'll get to that at the end of the chapter. But the idea here is when we have a saturated solution, we have the solid dissolving and we have crystallization happening at the same rate. So the same idea here. If I add, let's say, Cl minus in the form of HCl, if I add this, Le Chatelier's principle predicts which way the reaction will go. To the If I add Cl minus, it should go to the reactants. So what should you observe? If I add a little bit of Cl minus, if I make more reactants, the reactant is a solid. So wouldn't we see more solid being formed? Okay, let's see if that happens. All right, so maybe I can do this. Oh, I have to put the hood on. Let's see if that happens. So I have a near, there we go, a near saturated solution of sodium chloride. It just looks like regular water, all right? So I need to do this. I need to wear gloves because it's concentrated HCl. So if I add Cl minus, that's a product, I'm going to push it towards the NaCl solid, so we should see, hopefully, a little bit of solid being produced. And then they gave me a lot of acid, so I can dump a bunch, and then maybe we'll see a lot of solid come out. Okay, so HCl. Do I have to mix it? Oh, I do see solid coming out. I see it. Do you see it? Probably not. Let me add some more. Do you see little bits of solid swirling at the bottom? Do you see it? Kind of? No? Do you see? I don't know. Do you see it? Like, oh yeah, you do. Right? Here. Do you see the little white bits at the bottom? Okay. So we are pushing the equilibrium to the reactant side, forming more solid. So that was just a little bit of HCl. So they gave me like a huge hunking amount. All right. So if I put so much Cl minus, I can make a bunch of solid kind of come out at once. And that's because I'm adding product, pushing it towards the reactants. Okay. Concentrated HCl. Da-da-da-da-da. Did you see the solid form? Did you see the solid form? Yeah, so in this, we added product, it pushed it towards the reactants. In this case, it was very clear you could see the reactants because it was solid, right? It's a solid there, okay. Good? But really all it is Le Chatelier's principle. Because you can imagine if we added more Na plus into solution somehow, like if we added sodium nitrate, we would see the same exact thing, right? Because we're just adding a different product, pushing it towards reactants. Okay, so that was a lot of solid. That's a lot of solid. Okay. So that's kind of the qualitative idea behind the common ion effect is, Le Chatelier's principle that we've been doing all of this time. But we're going to do the calculations for it as well, because a buffer is also a basically application of the common ion effect. Okay, so there we go. Add blah, 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 which way we will shift towards reactants. Okay, so let's revisit the acetic acid equilibrium again and how we can make a buffer. So note, we have this Ka expression. We have Ha becoming A minus plus H plus A minus. Right? Chapter 6. I can ask you, what is the pH if I have, some concentration of Ha? You can calculate that, right? Ka, x squared over 0.1 minus x equals Ka. So that's my strategy there. Like if I gave you, you have the pH of, what's the pH of this concentration of HA? You put that into an ice table, you do this, set it equal to Ka, you calculate X is equal to H plus, you get pH. Also in chapter 6, I gave you, what if I give you the conjugate base instead? Like I give you 0.1 molar Na acetate, so sodium acetate, it's the same idea, ice table, x squared over the same thing, but it's equal to Kb for that you convert from Ka, you get x equals OH minus to get POH to get pH. Now in, oh wait, that's what this is, right? Yeah, that's what this one is, sorry. that I can ask you, what is the pH of this solution given of the conjugate base with this given solution? You use Kb, you get OH, POH, and then H+. So now the idea in this chapter, all right, in the last chapter was like, you only have this or you only have this. Now the idea is, well, what if you have both in the solution at the same time? That's a buffer. The idea is we have the common ion effect occurring in this place when we have both of them happening present in big quantities at the same time. Because, you know, we said when we put acetic acid into water, it dissociates a little bit. So there's a little bit of conjugate base there. But the idea is if we add significant amounts of both HA, the conjugate acid, or the acid and its conjugate base at the same time, we can essentially stabilize that H+ concentration. That solution is more resistant to pH change when both your acid and conjugate base are present at the same time. And that's essentially what a buffer is. We have both present at the same time in measurable quantities. I'm not just talking about Ka, because yeah, when you put acetic acid in water, it dissociates a little bit, but I'm not talking about that. I'm saying, like in this example where I put like HA plus its conjugate base in like into two separate steps. All right, so this gives us the idea that we can now have these mixtures of acid and its conjugate base in solution. That's creating a buffer. There's two big ways we can do that to make a buffer. I can do it like I did in this example. I can start with acetic acid and I can throw in sodium acetate, right? I'm straight up adding HA and A- into solution. So that's this. This is what I did. I can, or here, you can literally in your beaker put HF and NaF into your beaker at the same time. That's for an acid. You can also do the same thing for a weak base. So if I have a solution of ammonia and I add ammonium chloride, I'm literally putting the conjugate acid of ammonia in there. And so what I'm doing is I have both ammonia and ammonium in solution at the same time. For the previous one, I had HF, my acid, and F- in your beaker at the same time in high amounts. So that's one way to add a buffer, to make a buffer. You literally add the acid and the conjugate base, or the base and the conjugate acid, in their forms together in one beaker. Another way we can make a buffer is the idea that we can partially neutralize an acid. Okay, so when we neutralize an acid, and I mentioned this, we can neutralize it with a strong base. So note the arrow I have here. This is a different type of arrow. We haven't seen one of these guys in a long time. This is just a full-blown reaction arrow. So if I start with some amount of acid, and if it's monoprotic, shouldn't it take one equivalence, like 1 mole of base, to neutralize all of it? The idea here is, well, what if we only partially neutralize it? Okay, so if I only neutralize half of my HF, then I'll have made half a mole of F- on the other side as well. So in doing that, I'm essentially doing, putting HF and F- in the beaker at the same time. I'm just doing it by neutralization instead. All right, and so under this line, this is basically how titrations operate. Titrations, where we add either a strong base or strong acid, we partially neutralize it, and in the end, we still have HA and A- in the beaker when we partially neutralize. Then the harder thing is for the base. We can do the same thing for a weak base. We can have a weak base in our beaker, start to add a strong acid like HCl, we neutralize it as well. So here's that neutralization reaction. Note the arrow here. This type of arrow, we use a BCA table to see mole amounts and how things are consumed. So if I start with a mole's worth of ammonia and I add 0.2 moles of HCl, then I only produce 0.2 moles of my conjugate acid. But I consume 0.2 of my ammonia, so I only have 0.8 left. So with titrations, there's a lot of math, okay? And we need to be understanding, how to navigate Ka and Kb reactions, but we also need to go back to our stoichiometry and how to navigate BCA tables and recognize what is in my beaker based upon the amounts given, right? If I have 50 milliliters of this, 50 milliliters of that, and I mix it, figuring out what's the limiting reactant, what's left over in the reaction is a very important skill going forward, all right? So in this chapter, we are looking basically at mixtures of these things, that there are different ways to get an acid and a conjugate base into solution, 2 different ways. So in chapter 16, again, we just looked at what if you only have HA in solution. We used our Ka expression. We've already did a billion of these. You set it up like this. You set that equal to Ka. You get X, that equals H plus. You plug that in to get your pH. And so the idea here is, well, now we can make buffers. We don't just have pure HA in solution anymore. We can add the conjugate base deliberately to the solution so we can buffer these solutions so it can resist pH change. Our bodies were just big buffer bags. Okay, you don't want to drink a acidic soda and like the pH of your blood spike, okay, because then you die. So we are just big buffers, right? We want to resist pH change when we eat acidic foods. Most foods we eat are acidic. We like acidic tasting things. Basic things do not taste good to our human tongues. All right. So chapter 17 here is using the common ion effect to still calculate pH. So instead of just starting, when we did our ice table, we always had like some amount of that, 0 of everything else. The idea here is now in the initial line, we have amounts in 2 places, but it still works the exact same way. So here we want to calculate the pH of this solution of acetic acid, and we add 1 mole of its conjugate base. So if it's in 1 liter, wouldn't this be 1 molarity of A minus? Okay. So it's the same exact thing. We just need to put those values in the ice table in the appropriate place. So for HA, I'm going to put 0.1. There's 0 H plus. And there's 1 of the acetate, the conjugate base. So see how it differs, like right here, because we just have conjugate base present in a measurable amount. So before we even do the calculation, we started at a pH of 2.9 or whatever. If we add the conjugate base, which way should the pH change? Don't look at the answer. If we add conjugate base to this acid, like that's what we're starting with, it should go up. Let's hope it goes up. All right, so what do we do next? We have the initial line, minus X, plus X, plus X, minus X. How do I know that the reaction has to go to products? There's 0 and H plus, very good. Okay, so plus X, so we see at equilibrium at 0.1 minus X, we have X, and then we have 1 plus X. What do we do next? Ka, we put into the Ka. Okay, so Ka equals X times 1 plus X over 0.1 minus X equals Ka, and that's the number. Oh, my handwriting's really bad right now. There we go. What do you think we can do next? Do you think we can neglect those X's? Yes, we can. Yay! Yes, we can neglect those X's. So for these buffers, because the concentrations of the buffers themselves is so big, like if we go back here, if you calculate X in this chapter 6 type question, you get X is a really small number. It's a pretty small number, and so it'll probably be pretty small in this case too. So for buffer questions, we can usually neglect X. And I mean, you can try it yourself. Plug this whole thing into Wolfram Alpha. Why don't we just do that? You want to do that? Plug it into Wolfram Alpha. Okay, let's do it. Okay. Oh, you don't want that. Wolfram alpha. Okay. Okay, what was it? X times 1 plus X over 0.1 minus X. Okay, thank you. Equals 1.8 e negative 5. Okay. All right. There's X. Do you see X right there? Someone write that down. Someone write that down. 1.76 times 10 to the negative 6. Now I'm going to take the X out of the concentration changes. So I'm not going to get rid of this X, this one right here. I'm not going to get rid of that one. I'm only going to get rid of the ones that are in the parentheses. Let's see what the answer is. Where is it? Where is it? Oh, right there. Result? No, right there. 1.8 times 10 to the negative 6. Is that the same number? Yes, it is. Yay. Thank goodness. So if you ever wonder if you can neglect X, I always just do that. Okay, I put the whole thing into Wolfram alpha, and I start taking X's away and see if I basically get the same number. And we do. So yes, we can get rid of the X terms. And so how this simplifies is I get rid of that, I can get rid of that. So this becomes X times 1 over 0.1 equals Ka, 1.8 times 10 to the negative 5. And what did it say the answer was? X equals 1.8 times 10 to the negative 6, okay? Molarity, and again, we're playing the same dance here. X is equal to what? H plus, because that's what the ice table says. And so then that's how we get our pH. This is H plus concentration, and then that's our pH. So based upon that, does that match our intuition that the pH went, after we added conjugate base, the pH should go up for 2 reasons. We're adding a base to the solution, but we're also, disrupting this equilibrium. We're adding base, consuming acid at the same time, so the pH should go up. All right, so what we just did here, this is the Henderson-Hasselbalch equation, right, what we just did. Where we just took, because let me just go back here real quick. All right, so in this equation where we did X times 1 molarity times 0.1 molarity, X is equal to H plus, right? Like we said that. 1 molarity is equal to the concentration of what substance? A minus, right? That's how much A minus we added. 0.1 molarity is the concentration of what substance? HA. What is that? This is the Ka expression. The assumption we're making is that the actual amount that we're adding to the solution, this is what I call the analytical concentration. It's how much you're actually adding, like based upon mass or molarity to the solution, is equal to the concentration of A minus and HA at equilibrium. That's the assumption we're making, that the tiny plus X minus X terms don't really make a big difference to the analytical concentration. And that's what the Henderson-Hasselbalch equation is. But all these guys did was they just took the negative log of both sides of the Ka expression and they got a whole equation named after them, which is stupid. Okay? So the Henderson-Hasselbalch equation is the same exact thing. It is the Ka expression. It is the Ka expression. We're saying that the pH of the solution, which is the H plus concentration, equals pKa. Do you remember what pKa is? Negative log, because P just means negative log of Ka, so negative log of the Ka value. So essentially, Ka is that, so pKa equals negative log of 1.8 times 10 to the negative 5. I think that's equal to 4.7447, I think. I've done enough of these that I just know them. And I think you will too, here soon. A lot of things we do is with acetic acid. And so that's the number that goes into this pKa place. It's a constant all the time, depending on what substance you are and working with. And then we add log of the ratio of the concentration of base over acid, the analytical concentrations that we put into solution. All right. So that's the Henderson-Hasselbalch equation. It's just the Ka expression. All right. Is that it? And so we get this when we neglect the plus x and minus x terms, which we're allowed to do. It's basically the same number because these analytical concentrations are very, very big. Yeah, but this equation doesn't work when things are very dilute. So when you're outside the scope, but all that's outside the scope of this class. So kind of like how we did the strong acid, very, very dilute strong acid. It's the same thing here. The Henderson-Hasselbalch equation breaks down at really dilute concentrations, but we won't do that. We will always neglect X. Okay, so let's do some questions. So we're going to navigate the Henderson-Hasselbalch equation. So we have a buffer. With that pH, we make it using acetic acid and sodium acetate. What is the base to acid ratio? So we're just plugging in everything we know. So pH equals pKa plus log of base over acid. Do note, so see here how it says concentration of base, concentration of acid. If both of those substances are in the same volume of water, that ratio is also moles of base over moles of acid. It's the same thing. Because if both of them are in like 100 milliliters, you just divide both the numerator and the denominator by 100 and it cancels out. So this is a way you can kind of do calculations faster and recognize only when you're using the Henderson-Hasselbalch equation, you can work in moles as well, and you don't have to worry about the volume of water that it's in. And we'll do some examples here. So, all right, so we just plug in the stuff we know. So pH is equal to what, given this question? 4.7. pKa, I just gave it to you there. Again, it's just negative log of that Ka value. So it's 4.74 plus log of that base to acid ratio. So that's what we want there. So if we subtract things, we get log base over acid equals negative 0.04. How do I get rid of the log? We take 10 to both sides. Okay, so the base over acid ratio will equal 10 to the negative 0.04, whatever that is. I think it is 0.912. That's what my calculator says. I hope you can do this too. Put in your calculator, get that number. Okay, so based upon that number, so we got 0.9 something. So to make this buffer, just based upon that number, what is present more? The base form, acetate, or the acid form, HA, acetic acid? Which one's present in a higher quantity based upon that number? 0.912, which equals B over A. The acid form is more present, right? Because it's a number that's, so imagine this, if they were present in equal quantities, the ratio would be equal to 1. So if A is, there's a little bit more A, that means your denominator is more present, so there's more acid. But yeah, okay, yeah, so there's a little bit more acid present based upon the number that we have. Okay, so now this next question, how many moles of acetic acid should be added to 500 milliliters of 0.5 molarity sodium acetate? So that's telling me the A minus concentration. So I want to know how many moles that is. So 0.5 liters times 0.5 molarity there equals 0.250 moles of A minus. So that's how many moles of A minus I have. So now I can use this ratio here that I got. Basically 0.912 moles of B equals 1 mole of A. That's what that ratio means. And so from moles of A, the value that's present in that solution, I can use that ratio. Oh wait, no, that A minus, sorry. Yes, A minus. So I should be a little bit better here. So this is moles of the base form. So on the top is moles of A minus. The bottom is moles of the acid form. So this is moles of HA, the acid form. So when I do my ratio here, am I going to put the 0.9 on the top or on the bottom? On the bottom, because this is 0.912 moles of A minus, which is the base form. That's what base over acid means. It's the base form. So another way to think about this, so I was maybe a little bit too lazy there. Base over acid also, it's the A minus concentration over the HA concentration, where A minus is the base form. HA is the acid form. So I'm going to put the 0.912 moles of A minus on the bottom and then 1 mole of HA on top. And that will tell me how many moles of HA to add, how many moles of acid to add. I think it is something, what is it? 274 moles of HA is how much we need to add to half a liter of half molarity sodium acetate to give a pH of 4.7. That's how much, that's what that means. Kind of putting it all together there. All right, so let's do, we have a couple more minutes, so let's do another question. Maybe one that's a little bit more straightforward. Let's calculate the pH of a buffer that is this concentration of ammonia, this concentration of ammonium. It's a buffer, so what equation do we use? The Henderson-Hasselbalch equation. So pH equals pKa plus log base over acid. So before we go through this, let's look at the pieces of information. The 0.15 molarity, is that the base form or the acid form? Base. NH4 plus, that is the acid. Okay, so now you see how the ratio will come about. Let's see the other pieces of information. Am I given pKa? Not really. I'm given pKb though. Can I just take the negative log of this and stick it in there? No, I can't. Because if I take the negative log of Kb, that will give me pKb. So what do I need to do first to turn this into pKa? Do the Kw thing. So Ka for ammonia equals Kw over Kb. So this A is very important in the Henderson-Hasselbalch equation. We need to convert this to Ka first. So 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5 is Ka. That equals 5.55 times 10 to the negative 10. Now I can take the negative log of that and it'll give me pKa. So pKa is equal to 9.255. I just did more sig figs for fun. Okay. Or also recognize you can take the pKb, so you can take the negative log of this number and subtract it from 14, and you'll get the same number. Because that's just how the Kw expression works. All right, so so what you'll see here is for ammonia, pKa plus pKb equals 14. All right, so this is the number we plug in here. So pH equals 9.255 plus log of, what goes on top? What number goes on top? 0.15, 0.12. All right, and so that ratio there is, I don't have it, but, well, actually, before I even calculate it, do we predict that the pH will go up from 0.255 or down from 0.255? Up. Why? Because there's more base present. Yep. And so that's what you get. If you plug that into your calculator, you get 9.35 is the pH of that buffer. So it's a little bit higher than that pKa. And the reasoning is because there's just a little bit more base present based upon the concentrations. Okay. So we have 1 minute, but this one, recognize, and I'll go over this, that we have the same thing. We have NH3, our base. We have NH4, our acid form. So that's our BH plus, our acid. Okay. If you calculate how many moles of acid and base are present, I think you get that there's 80 millimoles of NH3 there, and that there's 80 millimoles of our BH plus. So when you put these two numbers, 80 over 80, in our log, you get the ratio is 1. The log of 1 is equal to what? Put it in your calculator. Log of 1 is 0. Yes. So this is special for this scenario. When your base concentration equals your acid concentration, your log, that ratio is 1 and it equals 0. So at this concentration, oh, I already have that here, that your pH equals your pKa value. And so that's what we get. I think that the value you get when you plug everything in is 9.26 or whatever is your pH, because base equals acid. All right. So I'll just leave you to that. We'll continue here on Friday and we'll start our titrations. I implore you to practice those ice tables. All right.